I am Justin Sampson. I've been a software engineer for over 20 years. And just recently went back to grad school in computer science at San Francisco State, focusing on ethical issues in artificial intelligence. Most ethical issues in artificial intelligence that we can focus on are very practical things like bias in our machine learning models or data privacy issues. But looking a little further into the future, there are also issues of moral agency. When do we recognize an artificial intelligence as being a moral agent, being responsible for its own decisions? And consciousness comes up in that discussion fairly naturally, because it seems like some kind of self-awareness should need to be there if we're going to recognize moral agency in artificial intelligence. But I didn't really imagine that I could do a computer science thesis on consciousness until last summer I stumbled upon an online conference about integrated information theory. And at that conference, Larissa Vantakas gave an introductory presentation about IIT. And in that presentation, she just kind of offhand mentioned that there was some research done on whether a computer could ever be conscious at all, according to IIT. And this question certainly intrigued me. Can a computer ever be conscious? Is there a way that we can say yes or no about that? The paper that she was mentioning is not quite yet published, but it's been presented at a couple of other conferences. Here's a link to a short description of it, short summary of it. It describes a dissociation that can be found between intelligence and consciousness. The idea being that you can have very sophisticated, complicated artificial intelligence that still wouldn't be conscious. So this intrigued me. I struck up an email correspondence with Larissa, sharing some ideas that I had about how maybe we could approach this in some different ways. She was very gracious and sharing additional materials with me. I went back to my advisor at San Francisco State, and he said, let's actually ask Larissa if she would co-advise a thesis. And she graciously agreed to that. So that's been wonderful to be able to have an IIT expert as a co-advisor on a thesis that's exploring, kind of taking my software engineering background, some of the intuition that I have about how computers work and how programs work, and see if I could potentially come up with a slightly different approach, see if we can make progress towards some kind of recognizing some degree of consciousness in artificial intelligence systems. IIT focuses on, for finding consciousness, wants to look at the causal structure of a system. And this is very important, and actually not something that I'm challenging at all in my approach. The idea of causal structure being important is that what we care about for consciousness is how a system matters to itself. So we want to look at what are all the elements of the system, how do they interact with each other, what are the cause and effect powers that different parts of the system have on each other. Here's an example on the left of a typical causal model that shows up in IIT literature. This system of P, Q, and R as Boolean gates connected to each other. We run the phi calculations for this. I ran this using the phi library that's been mentioned earlier. We get 2.31 as the phi value for that system on the left. Phi is giving us a measure or a degree of integrated information in a system. How much do the different parts of the system relate to one another? And this system, even though it's super, super simple, has a non-zero phi value. And of course, an actual brain presumably would have an astronomical value of phi, but IoT gives us this way of looking at different kinds of systems. And say even simple systems might have a very small degree of integrated information within the system. I'm able to construct, though, a functionally equivalent system, which is shown here on the right, where if we only look at the P, Q, and R elements of that system, it will have exactly the same state transitions as the system on the left. And so at some kind of functional level, we might say that those systems are functionally equivalent. That you can set up the system on the right in a certain state such that for any state on the left, you can get the same sequence of states in the system on the right. So that's a functionally equivalent system. but it has a very different causal structure. Because whereas the system on the left, those P, Q, and R elements are feeding into each other, the system on the right has a very different structure on the bottom that's really just reflecting the whole system state transitions of the system on the left, but in a much simpler and straightforward, more step-by-step kind of approach. And then the P, Q, and R values are just sort of computed from that. They're just, what we say, a feed-forward logic taken from the state of that system, the sort of portion on the bottom. And in fact, if we take this whole system, its phi is 0, has no integrated information, because there are multiple portions of the system that are feed-forward and therefore not feeding back on themselves. The lower right, there is a ring of 3 gates that if you take that in isolation away from the others, we get phi of 1 for that. But the system as a whole, there's nothing, no part of the system has that phi of 2.31 that you saw for the system on the left. So this is a very critical distinction between the causal structure of a system and what we might consider a functional equivalence between systems. And that distinction is not one that I'm challenging at all. Actually, very much find compelling the emphasis on causal structure in IIT. The idea that what matters is how the system matters to itself, not so much what it's perceiving or how it's behaving. If you're dreaming, you're still conscious. If you're in a sensory deprivation tank, you're still conscious. And so that distinction is very important. The question that I'm then tackling is, if I write a computer program that simulates a system on the left, is that computer program running on a computer going to be more like the system on the right or more like the system on the left? What do we mean by a conventional computer architecture, sometimes also called von Neumann computer architecture? There's some kind of a processor that's general purpose, central processor in the middle that's connected to some memory and some input and output units. Let's see. I'm going to simplify this down a bit for my analysis. The paper that I mentioned earlier by Findlay, Marshall et al. Had a sort of a toy computer architecture that they were analyzing, and I've come up with also a toy computer architecture, but perhaps a little more realistic that we can move forward with. In a simplified architecture, well, for the memory, we're just going to have ROM, which is read-only memory, where the program is going to be stored. So the processor will have a few registers. Registers are little bits of memory that the computer uses for sort of its active work. And we're going to cut out the I/O, input and output, because again, we're just interested in how the computer is running itself. We're going to keep a clock, which I'll talk about in a moment as well. And the challenge, sort of primary challenge in IIT for finding the causal structure in the system is that we need to be able to find, let's see, IIT defines, has a notion of black boxes where you can take a low-level description of a system and group low-level elements, micro elements of the system, into macro elements of the system in order to potentially find a greater degree of integrated information at some higher level. And in a system like this, the simulation that I'm suggesting is that the registers that I have defined are, there's an A register, which is that's going to hold the state of the system that we're simulating. So if we were simulating that PQR system, that'll have 3 bits for those 3 bits of that PQR system. B is a register I'm using as a temporary register to compute the next state of A, and then I is an instruction register that's going to be counting through the instructions as they are executing. And the challenge then is that those bits of the A register, which are the state of the simulated system, those nicely serve as sort of the output elements of black boxes in IIT's terminology. But then we need to actually be able to group all the other pieces of the system, all the other transistors and logic gates and so forth, into one of those 3 black boxes in order for the whole system to work and show the causal structure of that original system that it is simulating. But all of the other parts of the system, the instruction register, the logic unit, the ROM, those are all shared. They're not strictly tied to one or the other. So that's a challenge that we have to overcome. One point I want to drill into is on the read-only memory. Thinking about the structure of read-only memory. The ROM, this is true for RAM as well, which is read-write memory. Close to this, but it's a little more complicated, a little more subtle to argue. Essentially, the ROM is a tight grid of wires inside a microchip. Each intersection of that grid is a potential is a bit of data. If there's a diode present at that location, that's a 1 bit. If there's a no connection, then that's a 0 bit. And the CPU, when it wants to get a piece of data from the ROM, will apply a voltage to one of these horizontal lines, and then the diodes direct that voltage into the data lines. And so in this case, the CPU is reading the 4th location in the ROM and getting 00010110 coming out at the bottom. And the important thing here to note is, just as a general point, that may be interesting to there are other causal structure theories besides IIT, that you may think that a computer seems like a general purpose device, and it seems like a program is this abstract, a mathematical abstraction that you're not just giving to the computer to run. You might think that that means that the program doesn't actually change the causal structure of the computer. But in fact, if you look at how a program is actually run on a computer, it actually does require physical change to the computer in order to run a different program, one program or another. And so we do have to account for the program somehow in the computer's causal structure. Now, whether that gives us what we want in IIT or not remains to be seen, but that's at least the basic premise that we need to work on. My first step in analyzing a program was to as I said, I came up with a toy computer architecture with a very small instruction set, and the program on the right, which you can't quite read on the slide, and you don't need to, is a program to implement that PQR system. And there's code I have linked here that will actually interpret and run this, so we can prove that it gives at least functionally, the behavior of the PQR system when it is run. The interesting thing to notice about it, once I read out the program, was when I'm running the program, the first few instructions are all about computing the next value of P. And the next few instructions are all about computing the next value of Q. And the next several instructions are all about computing the next value of R. So there's this interesting interplay where, for a certain period of time, all of the computer's mechanism, the logic unit and ROM and so forth, are dedicated to computing the next state of one or another of those bits. And so there may be, it may be allowed in IIT that even if you don't find a complete sort of spatial region of elements for each of those simulated elements, as long as there's a disciplined way that at any given moment in time, each element is assigned to one and only one black box, that may be acceptable in IIT. We need to go further than this and get into how does each transistor map. So this is just sort of getting the idea going. And I've developed a procedure and code that would analyze a program like this and group it into groupings like this. So at least it's not like just an interpretation we're going to arbitrarily add in. We can have a disciplined procedure that actually finds this structure in a program. A couple of additional insights come up in looking at how does the program actually run. First of all, the clock we'll just accept as a background condition. In IIT, the way we focus in on what's inside the system is we hold everything else outside the system constant as a background condition. That can be a problem with the clock because the clock in the computer is oscillating, moving a low voltage and a high voltage. If we just hold it at 1 voltage, then the clock doesn't run, and obviously it's not conscious. But everything in the physical world is oscillating at some level. Neurons are firing at some rate rather than just being on or off. So we can treat a clock. The clock reads the background condition in a similar way, and that ensures that the computer is running. There's also an interesting distinction between flip-flops in a system. Flip-flops are elements in a computer that have a state of either an on or off state that lasts until the next clock tick. And then when the clock ticks, they take on their next state. Everything else in the system is all the transistors and logic gates in the logic unit and in the ROM, everything else are really subordinate to those flip-flop states. And when the clock ticks, then they all kind of catch up to that state of the flip-flops. Flip-flops are the individual bits, for example, in the registers. And that distinction gives us insight that we can move forward with developing a causal model of the computer that's just a little bit higher than the level of the individual logic gates and transistors by looking at the flip-flops as our actual elements. One example, a simpler example that I'll go a little further with is this one. This is a ring of two copy gates. So they are at each moment, copy gates are copying from each other in a ring. This is this is probably the simplest example of a system that will have non-zero phi in T. It has phi of 1.0 exactly. And on the right is a program that implements that in my toy computer architecture. The instructions are basically reading one of the elements, old state, and writing it to the new state of the next element, reading the old state of the second element and writing it to the new state of the first element, and then an instruction is just telling it to again repeat, keep going after that. So this is extremely trivial, and there's some issues with kind of interpreting how this would be extrapolated further, but at least gives us an ability to then look at what that causal model would look like if we take the individual bits, individual flip-flops in the registers of the CPU based on the program that's loaded into the ROM, and this is what we'll see. The A register here, as I said, the A0 and A1 are our simulated system state. I put little triangles there just to kind of draw our attention to which of those pieces is being, which of those flip-flops corresponds to the simulated system, and the I register is counting through the instructions. As you can see on the lower right, it points to which instruction it was currently executing. Now this is at the flip-flop level, so we're still not at the level of saying that this instantiates the causal model of the original system that we're simulating, but it gives us something that we can work with that's a little higher level than just the transistors and logic gates. And an important thing that I noticed out of this is that there's this kind of cycle where, I'll go back a little bit, whenever it gets to the beginning of the cycle, the A register holds the state of the simulated system, but everything else was set to 0. And so there's no like state hiding in anywhere else. The state that matters for going from here to four steps later being in the next simulated system state, what matters is the state of those A0 and A1 bits. So in some sense, there's, again, this might be interesting to other causal structure theories that I'm calling this a well-formed state, where we put the system into a state that has, the simulated system state is there somewhere, and the rest of the system is initialized into some kind of a state that doesn't depend on that state, is independently constrained. In this case, everything else is 0. And once it's in one of those well-formed states, after a few instructions, it'll be in again on one of those well-formed states. And importantly, that functional example I gave at the very beginning, where there's PQR on the left side and the functionally equivalent system on the right side, does not satisfy this particular constraint. So this is not strong enough still for IIT, because IIT really wants us to see that what are the, we need all of those elements to be assigned to a black box or another. But it's another insight along the way to say, here's something that gives us some causal insight about the computer. There's still some open questions about how well each of these kind of moves works. With IIT, they kind of all need to work together, and they need a little bit more detail as well. But this is at least some insights that I hope are helpful both in IIT and in other causal structure theories. And the main one being that the program is important in the causal structure of the program. So the fact that the computer is a general purpose machine shouldn't stop us from looking deeper for that causal structure. And if all of these insights actually do work together, then as long as the program's data, like having that PQR state in the actual register in the computer, as long as that's there, then we may very well see that actual causal structure for the simulated system. And therefore, according to IIT, it could be phenomenally equivalent to that simulated system. And if it were then an advanced artificial intelligence, such as a simulation of a brain, it could then be conscious as the brain is.
Thank you.
Any questions?